I'm going to switch directions now and come back to a fundamental concept to put in place, and then we'll bring it all together in the eddy flux equation, and that's the concept of continuity. And the concept of continuity is critical to the eddy flux discussion, because most people don't realize that what we're doing in an eddy flux measurement is a mass balance. It's basically what you did with Pat yesterday. You said there's so much mass going in at such a period of time, there's so much mass going out at such a period of time. We know that mass has to be conserved, so we do a mass balance, and you can calculate what must be going into the leaf or out of the leaf based on a mass balance. You do the same thing with an eddy flux system, even though there's no chamber there. We have to impose on it, every eddy flux system has imposed on it a virtual, what we call control volume. At the lower boundary, that's what you call your footprint, your flux footprint. But in 3 dimensions, going up the x dimension up the tower, you've got to have some depth to that footprint too, and that defines then a control volume. And what we're doing in the eddy flux measurement is we're doing a mass balance on some control volume that your tower sensors are sensing. And that control volume it'll extend linearly outward according to your footprint analysis, but really there's a depth to it as well that has to come out in the calculus, and you'll see that in a moment. So imagine some control volume, just some hypothetical volume with nothing in it. There's no leaf, there's no vegetation. And we have our UC, we have our flux density in, we have a flux density out. So the flux density in equals the flux density out. What's going to be the rate of change of concentration? Let's say this C is for CO2, a CO2 molar density. What's the change in concentration in the volume? 0, right? There is no change. Everything that's going in is coming out. So by continuity, there can be no change. But if we vary now, if we impose a divergence in those two, there has to be a change in the concentration in the volume to account for it, right? That's what we call that's continuity, the principle of continuity that establishes that connection. So in an empty chamber, no sinks or sources, F in equals F out, and delta C over delta T is going to be 0. We're at steady state, there's no change in concentration. For the case where delta T approaches 0, we can get into the calculus of the situation. So you can say that dC over dt equals 0. And I'm just slowly moving you from a finite framework to an infinite framework here, because we will work with the theory here in terms of calculus in a moment. Let's pause for a moment and consider this concept of continuity in a little bit more detail before we move it forward and place it within the context of the eddy flux. Most of you have been introduced to the relation between flux density and a difference in concentration through Fick's first law of diffusion, or some derivative of that law. And so we can write F, flux density, as equal to a conductivity, G, multiplied by a difference in concentration, delta C, where that difference in concentration is implied as occurring across some distance, x. In this case, the x is actually mathematically taken up into the parameter g. In the case of continuity, we're looking at the relationship not of the flux density itself, the absolute flux density, but the change in flux density across some distance. So we write delta F then over delta x to represent that spatial divergence in flux density is equal to delta C over delta T, the time-dependent change in the concentration of the control volume. So let's put that again into our illustration here of our hypothetical control volume. And we're looking now at the relation then between the flux density going into the control volume to that coming out of the control volume across a distance, delta x. If there's no difference in those fluxes in and out, then the change in concentration over change in time will have to be 0. What's going in is coming out. And that's the condition of steady state. If there is a difference, a gradient in flux density, however, in this case we'll say that difference is actually linear, and therefore we can just look at the mean divergence. We can write that as delta F with an overbar, where the overbar is referring to the average change in flux density across that distance, delta x. Then we can relate that mean difference, mean spatial divergence, to the mean, to the time-dependent change in the mean concentration that occurs within the control volume. And that gives us ultimately our continuity equation. So now let's put a canopy into that hypothetical volume. Let's put a bunch of spruce trees in there. And let's imagine that, I haven't put a tower here yet, but let's imagine that we can measure the flow of some scalar entity, CO2 or water vapor, in the side of that volume, and some flow out. It's got some finite distance. So you can set up this mathematical relationship. The flow out is going to equal the flow in plus any change in flow per unit change in x integrated across that delta x. Right? See the algebra there? This is what we call a divergence, a flux divergence. So basically there's been the surface, the biological activity at the surface has imposed a divergence on the flux through this control volume. And the divergence in calculus is defined as the partial f partial x over dx with the integral across that linear distance x. So we're defining that integral with respect to x. So then we can set up a very fundamental mass balance relationship that says that the flow in, remember this is how we defined the flow out, right? So the flow in minus the flow out has to be balanced by some change in some time-dependent change in concentration in that volume. The difference between the flow in and the flow out has to be balanced by a change in concentration in that volume. And we've referenced everything to the x-coordinate here to keep the calculus in line. That's a fundamental mass balance equation. That's simply saying if there's a difference between in and out, it has to be in the concentration change in the volume. And so you can just simplify that. I mean, f in minus f in, you can remove that. You can remove dx from both sides. Do some algebra, you have what we call the fundamental continuity equation, which is expressed as that. Basically then, any flux divergence across space has to be balanced by a time-dependent change in concentration.
You can also make measurements at the leaf level. And that's what we're going to talk about today. We're working at the leaf level. That is the interface between the atmosphere and the plant. The stem, the bowl, the rest of that, not so much. There is a little gas exchange that occurs there, but right there at the leaf level is where the gas exchange occurs. So in the 6400, we have a set of variables that we measure. We measure CO2, light, flow rate, water, and temperature. And why are all of those important? I gave you most of the answers early. CO2, why do we want to know CO2? We want to calculate what's the CO2 flux, what's the photosynthesis. Same thing with water. We calculate what is the transpiration rate. Why do we need this flow rate? Well, it's that what allows us to calculate what has been entering the chamber, and it's that time constant. So if you've got a slug of air that moves from outside through the box and then out, if you measure it before and after, you know what happened inside the box. And that's what an open system does, is we have a slug of air that we measure. We know how fast it's moving through. We know what the CO2 concentration entering, the water concentration entering, and we know what the flow rate going out, the water concentration out, CO2 concentration out, and we know what happened inside the box. Now, in a gas exchange system, the flow going from the green box, which is the console, through the tubes and out is not the only thing that's affecting what's going on inside the chamber as far as gases. What else is going on inside there is you have photosynthesis going into the leaf. So CO2 is going from gas phase to a liquid phase, dissolved, and then it actually becomes fixed in solid phase when it is fixed by the Calvin cycle enzymes. You also have E, transpiration. Water is coming out of that. It enters the chamber through the petiole, through the leaf, in the liquid phase, and then it evaporates to the gas phase. And so we actually have to account for what is that evapotranspiration addition to the chamber. Because this chamber is not a black hole. You can't just have mass go and not come out. And so what we do is we actually know what the evapotranspiration rate is, what the flow rate in is, and everything going in has to come back out. And so one of the assumptions we make is everything in through the mu and the E is equal to what is coming out. Okay? Make sense?
One of the reasons that this concept of continuity is so important to the topic of ecosystem atmosphere gas exchange is because we can apply it across a broad range of scales. We can use continuity within the eddy flux context to measure the exchange, for example, of CO2 between an entire ecosystem and the atmosphere, or we can apply it to a gas exchange chamber and measure the exchange between a single leaf and the air in that chamber. And so let's return to our control volume. In this case, again, starting from the empty state, and reminding ourselves that what we're doing is measuring a difference in the flux density of, in this case, CO2 going into the chamber and CO2 coming out of the chamber. We're relating that to the time-dependent change in CO2 concentration within the chamber. Well, now let's introduce a leaf into this chamber. And so in that case, the CO2 concentration in the chamber is not going to be allowed to increase. In fact, it's going to decrease because carbon dioxide will be going into the photosynthetic systems of the leaf. We can measure the difference between the flux density of CO2 going into the chamber and coming out of the chamber as S, the photosynthetic sink, in this case, of our leaf. And so we can write an equation for that photosynthetic sink as S is equal to the difference in the flux densities in and out of the chamber divided by the leaf area that's in the chamber. And so now we have an expression for the net photosynthetic rate of a leaf. So here's sort of what we're facing then in the case of a canopy flux, of an eddy flux. We've got a virtual control volume, hypothetical control volume. It's so fundamental that students who study eddy fluxes understand that ultimately this is a mass balance of a control volume. It's not, you're not going out there and magically just measuring every wind motion that comes by and adding them all up and getting a flux. There's a fundamental physics behind a control volume and a mass balance and a conservation of mass that underlies that flux measurement. And so I'm trying to build up toward that so that you get that into your minds, that there's a virtual control volume, just like there's a chamber over a leaf that Pat was giving you. There's a virtual control volume over some chunk of real estate out there where your flux tower is, and you've got to mass balance that. It's all got to balance out.